Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series, and this time a very important topic as well. And the topic is importance of grounding and the different types of grounding schemes that we have in power system network. My good name is John Kweku Amuotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Okay, so over here, basically at the end of my presentation, if you watch this presentation series and you like it, you select the like button in YouTube. And also, don't forget to share. And also, you can subscribe my channel. And this is the name of my channel. Now, let's talk about the outline of my presentation. And the first item is, we'll talk about why grounding is needed in a power system network. And we'll talk about the different grounding schemes in an industrial facility setup and also a generation facility setup. Generation can be utility company. Okay, so now let's talk about why grounding is needed. And the first item that we can talk about is basically improving upon safety. Safety in the substation environment and facility switching station environment. Now let's take a deep dive into why improved safety it's needed. As you know, maintenance personnel, operation personnel, engineers, and construction personnel. And other personnel will be working in this substation environment that has the equipment. And there's something they call step and touch potential, right, which is based on ground potential rise. Right. So when basically they are going to build a substation, or let's say a substation is going to be upgraded or modified, they perform the earth grade studies, right? And it's based on a lot of parameters that are input into the simulation software to basically determine the ground potential rise. Meets the required criteria to basically prevent shock hazards that can be encountered based on step and touch potential. Next is pressure over voltage. So basically, the flow of fault current, right? Let's say from the faulted phase, and if it is coming here, basically you have the neutral and you have a resistance here, right? Basically, this resistance reduces the amount of fault current that is going to flow into the equipment, right? If let's say a transformer is right here, and the neutral of the transformer is grounded through this resistor, right? Or a reactor, right? Okay, so this reactor or the resistor limits the fault current to tolerable limit. So as such, basically it results in a reduced transient over voltage that can occur if this whole fault current is supposed to flow through the equipment, and it can cause damage. Also, grounding the neutral or grounding the equipment basically allows ground fault current to flow. Of course, there's a path for the ground fault current. As such, the protected relays are able to detect these ground faults as quickly as possible, and also provide the required tripping and isolation of the equipment within the allowable time to prevent damage to the equipment. Next, yes, of course, basically, if we are limiting this fault current, right, to the allowable limits that is supposed to flow into the equipment, right? Or let's say for low impedance grounding scheme, we are limiting the fault current between 100 amps to 400 amps, right? This is what is allowed to flow through the equipment without, and knowing that it is not going to cause any damage into the equipment, and will allow the protected relays to detect this amount of fault current based on the settings to isolate the equipment. Aside, it limits the ground fault and also prevents the damage to equipment. Likewise, for solidly grounded system, right? Okay, definitely, you don't have any um, resistance in the part, right? Okay, so definitely, that's a full um, fault current that is flowing. So basically, it has the relays being able to detect the fault as fast as possible to clear the fault as quickly as possible. Next, a source of ground fault current, right? Definitely. If you provide that path to ground, definitely it makes it possible for ground fault current to flow for protected relay elements, other metering elements, to be able to detect this amount of fault current. Especially protected relays that have a sequence of event, basically waveforms capture, to be able to capture this fault current and the subsequent waveform for the voltage. Next, let's talk about the types of industrial grounding schemes. And basically, like I made mention on the outline, basically I indicated that there are different grounding schemes that are implemented in the industrial environment, industrial facilities, and also in the generation utility facilities. So we talk about all these different grounding schemes that are applicable at all these facilities that I've made mention. Okay, so the first one is ungrounded schemes, right? Okay, so ungrounded schemes means that there's no path to ground. They're basically, the ground, the winding of the equipment is floating, right? A typical example is delta winding. And also you can have a Y that is just a floating and not connected to ground, right? So delta winding or Y connected winding that is floating and not connected to ground can have a straight capacitance to ground, right? This is invincible, but it's called imaginary capacitance, right? That basically is connected to ground. Okay, for the delta connected winding, you can also have this straight capacitance, right? Okay, so basically the winding of that equipment is grounded through this straight capacitance to ground, and it is called imaginary ground, and it's not visible. So basically, it's more of it is floating, and it basically offers a very high impedance, high impedance path to ground. Next is a solidly grounded schemes, right? And the solidly grounded schemes, an example is like this. If you have phase 1, phase A, B, and C, then the neutral basically is connected to the ground, right? Okay, so it's basically it doesn't have any impedance in the path. So this is what we call a solidly grounded scheme. Then you have a low impedance. So low impedance basically you have a resistor, right? With a calculated required resistance that is in the path of this. Or you can have a reactor too. You can have a reactor, right? That is in this path. Okay. So the goal of this impedance or resistance is to limit the ground fault current, to tolerable limits, for industrial facilities, 100 amps to 400 amps, right, before it flows into the equipment. Right. For industrial facilities, you hardly find high impedance grounding schemes, and because most of the high impedance derived high impedance schemes are mostly in the generation facilities. Okay, so another scheme that I think I can make mention here for industrial grounding is a zigzag transformer grounding scheme, right? Okay, so it is called derived neutral, right? Okay, so for instance, if you have a delta connected system, right, and there's a need to derive a grounding path for this delta connected system, then that is when you use the zigzag transformer to basically provide that impedance path to ground to be able to detect ground fault as faster as it is, because for these ungrounded schemes, usually most often than not, you use monitoring and visualization alarms to detect first time fault for the operator to take action and basically detect where the fault location is, But if the operator doesn't provide a quick reaction, then the possibility of a second fault can be very disastrous and can cause significant damage to the equipment. Okay, so this is an example of an ungrounded system. So, okay, as you can see over here, this is a Y-wound transformer, right? Okay, so you have the neutral over here. This is phase A, phase B, phase C, right? The neutral is floating. There's no connection to ground, right? So this is what they call an ungrounded system. So as you can see over here, the only connection to ground is this stray capacitance that I was talking about. It's imaginary, right? It's based on the insulation system of the winding, right? It's based on the insulation system of the winding, phase A, phase B, phase C, right? And as you know, if you have an insulation system, you have a conductor that is acting as an electrode. You have a ground plane, right? If this is the insulation, this is the conductor, right? It is basically acting, it basically forms a capacitor, right? So this is this straight capacitance that you're seeing over here, right? Okay. So if there should be a fault current, right? If there should be a fault, let's say on this phase, right? Then basically this is going to be the path of your fault current flow, right? Flows over here, then over here, right? So this is the path, and basically, show you, for this floating winding that is not grounded, this is basically, the flow path of the fault current. Okay, so now let's take a deep dive into an ungrounded system. What basically are the attributes and features. So as you can see, like I made mention that an ungrounded system, basically the neutral is floating. Everything is floating. It's not connected to ground, right? So the possibility of seeing a ground fault is very minimal, right? Even if you can see a ground fault, it is very small, right? It is very, very, very small because of the high impedance path that it offers, right? And very difficult to detect the first ground fault. Like I indicated that, usually a monitoring scheme or visualization alarms are utilized to indicate the first occurrence of ground fault, right? And that basically provides an alert scheme for the operator or the maintenance personnel to basically, listen to the alarm and take an action, to basically, identify the location of the fault and basically, take the equipment out of service. Because upon if a reaction is not taken to correct, basically isolate the equipment, then the possibility of a second fault can be very disastrous. Actually, can cause a phase-to-phase fault and can be very disastrous. Next is no current between the neutral point and earth, right? As you can see over here, in the previous slide, right? You saw that the only path to ground was through those stray capacitors. Those are imaginary, right? They are not visible, right? So that is the only path of ground fault current that you see. Then also it gives you the possibility, right, for no switching to take place, right? Okay, so basically ungrounded systems mostly utilized in an industrial facility setup basically is to allow the processes to continue. Let's say upon occurrence of the first fault, right? The equipment can still run, right? Until a second fault occurs, which basically can cause a phase-to-phase fault. Then the second ground fault basically results in a phase-to-phase fault, right? Then if a fault should occur on a phase, right, basically the other phases are going to see an elevated voltage, which can be equivalent to phase-to-phase fault. So the insulation system is built to withstand a phase-to-phase voltage. So that itself introduces an additional cost. Comparable to a wide ground, where basically the insulation system is built to withstand a phase-to-earth fault or phase-to-ground fault. It also requires a compulsory insulation monitoring, right? Okay, for the first fault until the second fault occurs. Like I mentioned that usually if the operator does not take any action during the based on the first fault indication, then a second fault occurs, then that can be disastrous, right? Okay, so, and it also requires the presence of maintenance of personnel to monitor and locate the first fault. Usually they have this portable fault detector that they use to basically identify, pulses. It's basically the fault basically emits pulses. So that's how they're able to identify and locate those the location of the fault. Then there's also the possibility of ferro resonance, right? Okay, so basically the inductance of the equipment, let's say for a transformer, and also the stray capacitance, and also if there should be a capacitance capacitive bank at a facility that is in close proximity to this equipment, then there's the possibility of a resonance being formed. Let's say also if there's a cable being connected to this equipment, with the cable insulation system basically forms capacitance, and that can result in ferro resonance activity. Next, an amplification of the voltage. Ferro resonance basically when it occurs, it just amplifies the voltage, and the voltage, amplified voltage, can be very fatal for the insulation system. Also, very difficult to implement selectivity, right? Because the fault current is so small that basically, you cannot achieve protective relays selectivity in that. Next is another grounding scheme that we'll talk about in industrial facility. It's a solidly grounded system, right? Okay, so for a solidly grounded system, basically you have a solid connection, right? No impedance or resistance in between that part. No, it's just solid, right? Okay, so you have a solid in between the neutral and the ground, and it limits the voltage rise on the unfaulted phase, right? Okay, so for a solidly grounded system, right, or the unfaulted phase does not experience voltage rise, right, which can be equivalent to phase-to-phase voltage. Okay. So the ground fault current is basically limited by the inherent impedance of either the generator or the transformer, right? The transformer has a leakage reactance, right? Okay, and the generator, if it is a generator, it also has a leakage a resistance and reactance, which forms basically an impedance, right? Okay, so that is the only thing that limits the ground fault. Other than that, there's no impedance in that part. Okay, then also absence of zero sequence impedance results in very large ground fault currents. Right? This type of connection basically it's for low capacity generators, right? If you, as you know, for industrial facilities, if you have a low MVA or KVA rated generators, and this scheme can be utilized. Now let's continue with solid grounded system, right? Okay, so because of there's no impedance in that part, it's very easy to detect the ground fault current, because the ground fault current it's so high, and because the ground fault current is so high, it can lead to an equipment damage, right? Okay, so, and it also requires a compulsory switching of a breaker to isolate the equipment upon the occurrence of the first insulation fault, and also it reduces the risk of overvoltage occurring. Also, because of it is basically connected to ground, basically you have a phase to earth voltage. So the insulation system of the winding is built basically based on phase to earth voltage rating, and that can also result in cost reduction. Next is there is also, because of the high current that flows, ground fault current that flows, there is the risk of a touch voltage that can be experienced by maintenance personnel and operation personnel or engineering personnel that might be in proximity, close proximity with this equipment. So this is an example of a solidly grounded transformer, right? As you can see over here, the wire connected winding is basically connected to it without any impedance in its path. And basically, in the previous slide, I made mention of all the attributes that are associated with a solid grounded system. Okay, so on the other hand, sometimes, in an industrial facility, right? Okay, or smaller generation facility, right? Let's say you have a generation plant that is very small, let's say, less than 100 MVA, right? 50 MVA, right? 25 MVA, right? Okay, you can have some of this typical example of this scheme, right? Okay, so as you can see over here, right, you have a Y connected winding over here and a delta connecting winding over here for this transformer, right? Okay, so for the delta winding, right? Okay, if the delta side is connected to this bus, right? Okay, so this bus could be, let's say, a medium voltage bus, right? Okay, so how do I detect for current for alarm and visualization, right? Indication, so basically I can connect a Y delta transformer, right? That can basically give me a 3VO, right, to be able to detect a broken delta connection to be able to detect ground fault on this bus, because like I indicated, there's a delta, right? Okay, so there's no path to ground on this winding. Now let's talk about low impedance grounded system, which is can be applicable to generators and transformers, right? In an industrial facility, right? Okay, so in this type of grounded scheme, right, it is either connected to a resistor or a reactor, right? And like I indicated, the goal is to limit the ground fault current to 150% of the generator nominal current. Okay, so usually the current after the ground fault is limited is about 100 amps to 400 amps, right? So let's say if this is the resistor or the reactor, and the ground part, right? After the ground, the fault current flows through the resistor, and if this is the neutral of the transformer or the generator, right? Okay, so what is left here should be about between 100 amps to 400 amps, and most industrial facilities utilize 400 amps. Then, mostly, used in industrial facilities, right? Okay, so let's say if you have an industrial facility that has multiple generators that are connected, right, to a bus, right, then they usually utilize this scheme, right? It provides a source of ground fault to the system. Yes, this basically a source of ground fault for the system as well, and also protective relay elements that are in the system. And the operating technique is basically when the fault occurs, you want to switch off the equipment. Yes, because to prevent further damage, and because of the resistance, it helps to dampen the any overvoltage condition. So it has a fault current limiting capability, like I indicated. The resistance in that part basically allows the fault current to be limited, and basically it allows selectivity, right? Okay, it's because you have the fault current basically 100 amps to 400 amps. So depending on the number of generators that are connected to the bus, right, basically it allows some selectivity to be achieved. Next is disadvantage includes a tripping of the fault current. Yes, definitely. If the fault current occurs, you have to identify it and trip it. Okay, and a high overvoltage can occur, right? Based on the unfaulted phase can experience an overvoltage condition, which can result in a phase-to-phase fault on the unfaulted phase. Then it also requires a compulsory switching, tripping on the currents of the fault flow. Next is a typical setup of low resistance or impedance connected generators that is in an industrial facility, right? As you can see, these are bus connected generators, right? Okay, so and it doesn't have any transformer, right? Okay, so basically low impedance grounded scheme is basically implemented to allow for selectivity, and also sometimes grounded 67 directional ground or 67N is utilized to detect the direction of the fault current, so that each generator can be tripped instead of the whole bus. Now let's talk about the grounding schemes that can be applied to generation facilities, right? Okay, so the first one is a low resistance or impedance scheme and high impedance scheme, right? Okay, so for smaller generation facilities, I'm thinking that the low impedance and resistive and grounding scheme is used, and for bigger generators, for larger generation facilities, it is high impedance grounding scheme. Okay, so for low impedance grounding scheme, I think I did go over this, and so basically the goal is a reactor or a resistor is connected in the path of the neutral and the ground, right? And the goal is to basically to limit the ground fault so that we can achieve between 100 amps to 400 amps, right? And can be applicable to generation facilities for single generators or multiple generators, and also provides a source of ground fault. So this is an example of a low impedance grounded scheme that is used in typical smaller generation facilities, right? Okay, so this is your AC grid or any bus that is connected to this generator, and this is basically the grounded resistor, and this is your grounded earth grid. Okay, so basically the choice of the resistance value is basically an optimization is implemented, right? Okay, so if you have a lower resistance, right, a good amount of fault current will flow, right? You also have to be careful on the choice of resistance because a higher fault current can lead to the more damage of the generator, and so as such that basically like I indicated, optimization is utilized to get a good value of resistance that can basically allow a good amount of fault current to flow. So between 100 amps to 400 amps or 200 to 400 amps basically can limit the damage that can be caused from this fault current into the generator. Okay, so this is also another example of two generators that are connected to a common bus, right? Okay, so they usually, but this one is called system, right? Okay, unit connected, because they are all connected to the system through a step-up transformer, right? On the previous slide, is bus connected. They call them bus connected because you have the two generators that are connected to a common bus. But this one is unit connected because they are connected to a common generator step-up transformer that steps the voltage up to a higher voltage before it is integrated to the AC grid. Okay, so now let's talk about high impedance grounded scheme. So in this scheme, like I indicated, mostly applied to very large generators, right? Very very big generators. So basically, the neutral, right, is basically connected through a distribution transformer, right? Distribution transformer that basically, and you have a resistor connected across here, and you have the relay, the 59G or 59N relay that basically, because of the high impedance, right, the amount of fault current that flows is very small. So that is why a resistor is connected across here to amplify the voltage to be able to, for this protected relay, voltage protected relay to be able to basically identify the fault and basically pick up and basically trip the generator, right? Okay, so as you can see over here, a resistor is connected across here basically, and based on using the turns ratio, basically it limits the fault current. So basically this one, you see that the fault current is limited from 5 amps to about 25 amps, and typically it's about 15 amps, so that's in between the range, so that is the amount of fault current that beyond this grounding scheme. This is what flows into the generator, right? So 15 amps will not cause any damage to the generator, and basically will flow until the protected relay is able to detect the fault and isolate the fault. Okay, so this is basically another scheme, unit connected, and a unit connected through a step-up transformer. This is the generator, and this is the distribution transformer, right? Okay, a step-down distribution transformer that basically have a resistor connected across it, and basically so this distribution transformer is acting as a neutral grounding transformer, right? Okay, so basically based on the reflected impedance principle, right? Okay, so the resistance of the neutral grounding resistor, and this is a reflected resistance. So you want to basically calculate the reflected resistance, right? And that is based on the voltage ratio, the square of the voltage ratio of this distribution transformer and this neutral grounding resistor, right? So that's how they calculate your reflected resistance, and basically based on the reflected resistance, you can calculate the amount of current that is flowing. So typically, about less than 10 amps or less than 15 amps, right? But the typical industry range is for high impedance is 5 amps to 25 amps. Okay, so like I indicated, so the 59N relay that is connected across this resistor for a high impedance grounding scheme, right? Okay, so it provides 95% static ground for protection, right? So the remaining 5% of the neutral, it's not protected, right? So there has to be an additional 5 to 10% that has to be provided by a different protection scheme, and usually they utilize the under voltage, third harmonic under voltage to complement the last 5 to 10% of this protection scheme to achieve an overall 100% protection scheme. Next is the hybrid grounding scheme, right? Okay, basically based on the criticality of the generator, right? Okay, and basically the investors are putting in a lot of investment to achieve a higher grounding scheme. Okay, so this basically has two grounding schemes that are combined, so that's why they call it hybrid. So it has a low impedance grounding scheme and a high impedance grounding scheme, right? Okay, so when the generator is in nominal operation without any fault, right? Okay, so basically the generator is connected through this path, right? Okay, but upon the sensing of a fault, right, that is when this ground differential relay basically identifies the fault and trips this breaker, trips the excitation system and the prime mover, right, and activates this grounding scheme. Then basically it basically comes into play and basically limits the ground fault to the required 5 amps to 25 amps, or let's say 15 amps or 10 amps, right, to achieve that selectivity. So basically, your goal is basically, during ground fault to be able to limit the ground fault to a lower fault current to prevent damage to the generator, right? Okay, so this switch over here basically opens up, right, during a fault, and basically the generator gets connected through this path. But on the normal operation, right, this path is basically out of the circuit and the generator is connected through. Okay, so with that comes to the end of my presentation, and I hope you enjoyed this beautiful presentation. So I'm pretty much sure by now you should know all the different grounding schemes that I employed in industrial facility setup, and also in generation facility setup. So don't hesitate to go to my YouTube channel, right? Okay, and as this is the title, basically of my YouTube channel, and there's a lot of videos there, that has a lot of learning tutorials that basically can help you with your career. And if you like my presentation, don't hesitate to select the like button, and don't forget to share, and also subscribe to my channel. With that, thank you so much for your listening ears, and look out for the next presentation. Thank you.